Hi guys. Today we're going to talk a little bit about hyperbolas. And so we've talked about parabolas, we've talked about ellipses. So now we're going to move on to our third conic section, which is a hyperbola. And so a hyperbola is basically when you have two parabola-looking things, but they're not actually parabolas, that kind of face opposite directions. So we're going to look at a couple cases, if they're left and right from each other, or if they're up and down from each other, are the ones we're going to look at. So first thing we need to do is come up with the definition of what a hyperbola is, how we create this shape. So the definition is the set of all points whose difference from two fixed points called the foci is constant. Now, if you look at this closely, you'll notice it looks almost exactly like the definition of an ellipse. The only difference is this word difference. See what I did there? So difference is the different thing. This was sum when we were talking about ellipse. So because of that, the equations look really, really close to how they did for an ellipse. So when we had an ellipse, this equation looked exactly the same except for right there was a plus sign. Because it was the sum of the distances from the two fixed points is constant. And so the only difference is we're changing that plus sign in an ellipse to a minus sign to make it a hyperbola. And so now we need to talk about what this means as far as the standard equation with the center at hk and what directions it makes it open. And so for a hyperbola, remember we got the two parts of a hyperbola. And remember our conic section we looked at the other day, it's when we cut it like this, and so we actually get one like this and one like that. So we have these two things facing the opposite directions kind of that go out. And so it's going to open two directions at the same time. Now, where A and B are, and which one's bigger, is actually irrelevant in this. I know that was a big deal for the ellipse. What's important to figure out which way these open is which term is positive. Do you notice on this one, the x term is positive and the negative is in front of the y term? This one, the y term is positive and the negative is in front of the x term. That's what determines whether this opens up and down or opens left and right. And so on this one, our x is the positive term. And so we don't have a minus sign right in front of this whole term with the x. So this one is going to open right and left. And then if we've got the y term being the positive term, notice the negative is in front of the x term, that's going to make this open up and down. So that's how we can determine which way one of these is going to open. And so let's take a look at one of these now, because I feel like to help with this, we need to see one of these. So let's take a look at what a hyperbola looks like and some of like the key characteristics in one. So I have kind of the stuff we're going to draw in to make a hyperbola in this picture so far. And we're going to add to this in just a minute. So we've got our center right here. And then we've got vertices and we've got co-vertices going the opposite direction of the vertices. And basically, what I have here would be how we get an ellipse. But instead of drawing an ellipse, we're going to draw a rectangle that goes through the vertices and the co-vertices. And then to figure out where to put the hyperbola, we're going to draw in the diagonals of that rectangle. Now, what those diagonals are going to tell us is where the asymptotes are. So we're going to have an asymptote and another asymptote that this hyperbola is going to approach. We've already talked about asymptotes. Remember, that's a line that a graph approaches, gets closer and closer to, but doesn't quite ever get to. And so if I want to draw in what the hyperbola looks like here, every hyperbola will always hit the vertices. And then I also have the foci drawn in here. There's a focus, there's a focus. And every single shape we've talked about opens around the focus. That doesn't change for this. And so there's one branch, we call it, of the hyperbola. So we've got one branch here. We're going to have another one over here because the hyperbola is always two of these. Here's the other branch of the hyperbola. So when I draw this, basically what I'm doing is I'm making sure it goes through the vertex, and then when it goes out from here, it approaches these asymptotes. So that's what the hyperbola looks like. Now there's a couple other things we're going to have to label in here that are important. We need to know what a couple axes are called. And so one of them is this. we make an axis that goes through the center, the vertices, and the foci, we call that thing a transverse axis. And then we also need to do an axis right here. This is going to be called the conjugate axis. Right, and then a couple lengths we're going to have to put in here as well. We've already used these same variables to represent lengths. They're going to be the same as they were in an ellipse. Distance from center to vertex, we're going to call A. So distance from center to vertex, that's our distance we'll call A. Distance from center to covertex, we're going to call B. And then distance from center to focus, we're going to call C. So those are the same as they were before, A, B, and C. A, center to vertex, B, center to covertex, C, center to focus. And remember, I only put these one direction, but it's the same. These are always symmetric, and so that's A, but this is actually also A, center to the other vertex, B, also B, C, also C. Now, this relationship, we had something that looked like this for ellipsis. For ellipsis, it was A squared minus B squared equals C squared, or B squared plus C squared equals A squared if you wanted to just do some algebra, rearrange it. On this one, do you notice which one's the longest of A, B, and C? Our C is the biggest of the three. And really, if I wanted to find the distance for C, if I just took this length right here, thinking of this like little right triangle right there, A and B are the legs, that distance just moves right there. And so really, the hypotenuse of that right triangle right there is C. And so A squared plus B squared, just the regular old Pythagorean theorem, A squared plus B squared equals C squared, works when we're dealing with a hyperbola. So this is going to be an important little equation that you guys are going to want to keep in mind while we're solving these problems, because if you are thinking, well, how am I supposed to figure out B if I only know A and C? This is the way to do it. You need to know that piece of information to find the third one. You can always find the third one if you know any two. All right, so let's look at a couple examples now where we try to put some of this into practice. So we're going to look at the first one here where we want to graph one of these and find the foci and the asymptotes. And for today, I'm going to stick with ones where the center is 0, 0. Tomorrow we're going to get into ones that are all moved around and see how that affects things, but for today we're going to stick with just center at 0, 0. And so this first one here, the reason we know the center's at 0, 0 is because, do you notice there's no K or no H on this? That means we haven't moved the center around at all. H and K are both 0, so the center on this one is just 0, 0. And as I come up with things on here, I'm just going to go ahead and put them in the graph over here. So we've got the center right there at 0, 0. All right? Some other things we know. This has y squared as the positive term. If y squared is the positive term, this opens up and down. Now you could just say y is the first term or y is the beginning. Sometimes people just say that. The only thing, I don't like to say that just because you could put a negative out in front of here and make that a plus sign, and that would change things. And so that's why I always say y is the positive term. So since y is positive, this is going to open up and down. So in other words, this is going to be a hyperbola that looks something like this. We just got to figure out where to put all the points yet. So this opens up and down. The other thing we're going to need to do here is figure out how far to go left and right, how far to go up and down to make that box. Now remember what these represent under here. These are the a squared and b squared, and a squared is always under the positive term. And a does not have to be bigger than b. And so a squared is 16, which means in this one a is 4. Now that's under the y, so that means I want to go up and down 4. So I'm going to go up 1, 2, 3, 4. Now the reason I know I'm going up and down is because that number's under the y. So 1, 2, 3, 4 down as well. And then b squared, the number under our negative term, is 9, which means b in this one is 3. And since that's under the x, that's how far I want to go in the x direction. So I'm going to go 3 to the right, 3 to the left. And what I've just come up with there is what I need in order to make this box. So I'm going to make a rectangle using those vertices and co-vertices that we just came up with. Right. Now, something else that can happen in this, I know a and b are really close to the same number in this one. A and b can be the exact same number in a hyperbola. In an ellipse, that changed it into a circle. In a hyperbola, that won't really make a difference. All that would do is it would make your rectangle you're making a square, and that's fine. And so a and b could actually be the exact same number under both of these, x squared and y squareds. And then the other thing we're going to do, like we saw on the drawing we had of a hyperbola a minute ago, I'm going to put in the diagonals of this rectangle. And that's going to give me my asymptotes that this graph needs to approach. And really, at this point, that's all we need to draw the picture in. Because to draw the picture, we need to know where the vertices are. We need to know which way it opens. We know this one's opens up and down because the y is the positive term. And so we're going to go from here and make it approach these asymptotes. From the vertex, make it approach the asymptotes down here. And there's a picture of that hyperbola. Now, we're not quite done. That takes care of the graph part. But we also want to define the foci and asymptotes. So to find the foci, we need to think about what C is. And this is where the a squared plus b squared equals c squared thing is going to come into play. We know a squared plus b squared has to equal c squared. We've got a squared and b squared already, don't we? And we could just put a and b in, but why not just use a squared and b squared since we've already got them? And so putting them into a squared plus b squared equals c squared, it looks like this. 16 plus 9 equals c squared. 16 plus 9, that's 25. So I have 25 equals c squared, which means c is 5. Now remember, in order to figure out should we be going up and down or left and right to get to the foci, every shape we've talked about always opens around the focus. This has to be the same way. And so since this has to open around the focus, we need to basically go up and down so that we're opening around the foci. And so C is 5, which means I need to go up 5 and down 5 to come up with the foci on this. And so that means the foci are at the points 0 and positive and negative 5. And you could write this as two separate if you like, 0, 5, 0, negative 5, but I'm just going to write it as 0, plus and minus 5. All right, so there's the foci. Now let's see if we can take care of the asymptotes. Now keep in mind, asymptotes are lines. And so this goes back to something we learned earlier this year, and you learned, many other years in math too, the y equals mx plus b, slope-intercept form of a line. And so let's see if I can find the equations for these asymptotes. And so I'm basically just plugging things into y equals mx plus b. Now remember, to find m, our slope, m is rise over run. And so let's do this line right here first. If I want to find the slope of that line, then I need to figure out how far did I go up, how far did I go over. Now in this particular case, I went up 1, 2, 3, 4, over 1, 2, 3, which means the m part on this is 4 over 3. And then we have to do plus b. b is the y-intercept. Now on this particular line, look at where this line hits the y-axis. It hits at 0. So if I really wanted to write that on there, I would just say plus 0. But I'm not going to bother because plus 0 doesn't do anything. And so the equation of that asymptote is just y equals 4/3 x. Now let's get this one right here. Now to get this one, I have to think again, rise and run. So my rise here is 1, 2, 3, 4. My run is 1, 2, 3, but to the left. And so the rise is positive 4, the run is negative 3. And so if I have 4 over negative 3, I can just put the negative out in front of the whole fraction. So I'm going to say the rise over run or slope on this one is negative 4/3 x. So putting it in y equals mx plus b. But look again at where this one hits the y-axis. So the y-intercept of this one again is 0, and so that's again plus 0. So there's the equation of both asymptotes. So there's the one asymptote, there's the other asymptote. So now we've graphed this thing, we found the foci right there, and we've also found the equation of both of the asymptotes. So that takes care of everything we needed to do for that. All right, and then one last example here I want to do. I want to see if we can go the other direction. So on this one, you notice I gave you the equation at the beginning, and we were supposed to come up with what the picture looked like based on that. On this one, you're going to have some information about the graph, and you're trying to write the equation. So we want to make something that looks like this, but with the numbers all in the correct place for this situation. So we have the foci at plus and minus 3, 0. So just using this picture, if the foci are at 3, 0 and negative 3, 0, which is where the co-vertices were on here, the center is always just halfway between the two foci. And the center is always halfway between the two vertices, halfway between the two co-vertices. It's always just halfway between all those important points. So if we have positive 3, 0 and negative 3, 0, the point halfway between those is 0, 0. So that means the center on this one is 0, 0. Now that's important for our h and k that we're going to plug into our equation. All right, another thing that we need to do here. We know that the vertex is at 2, 0. And if that's the case, that means this has to open left and right. Because if 0, 0 is our center, we're going 2 this way to get to the vertices. This thing is opening left and right. So this opens left and right. Now keep in mind what A, B, and C represent. A is distance from center to vertex. There's the center, there's the vertex. Distance from center to vertex is 2 units. And so in other words, on this one, A is 2. Distance from center to focus is C. And so the distance from center to focus is, in this case, 3 units, so C is 3. Now that actually allows us to come up with most of the equation already. The fact that it opens left and right means that x has to go first, or x has to be the positive term. And so there's h and k are both 0, so I don't need to do x minus a number the quantity squared, I just need to do x squared. You could say x minus 0 the quantity squared if you really like, but minus 0 is not necessary. And that's going to be over a squared. Remember, a is always under the positive term, and so a squared, if a is 2, a squared is 4. Minus, again, for k, for y minus k, k is 0, and so y minus k is just y squared. And then b squared is what goes under there. We run into a slight problem there, because do you notice we know a and c, but we don't know anything about b yet. So we're going to have to do something to figure out b. This is where our a squared plus b squared equals c squared relationship between those three lengths comes into play again. And so here's what we have going on in this, basically, if I put stuff in there. We have a squared plus b squared equals c squared. We know that's true. And so I'm just going to put the information we've got in there. So we've got 2 squared plus b squared is what we need to figure out and what needs to go in right there. So I'm just going to leave that as b squared. But we do know c is 3. So it looks like that. And 2 squared we get 4 plus b squared equals 3 squared is 9. Subtract the 4 to the other side, and I get b squared is 5. Now I could go a step farther and say that b is the square root of 5, but we really don't need to, because think about what we want in the equation. Don't we want b squared right there? And so since b squared is 5, that's the number that needs to go right there in the equation. And so there's the equation of the hyperbola that has a center at 0, 0, because h and k are both 0, has a vertex at 2, 0 because we made a squared 4, which makes a 2, and then has foci at 3, 0 and negative 3, 0 because making b squared this number makes that happen for c. And so using a and c, we were able to figure out b. All right, so there's a good start on hyperbolas. This will let you guys do the first day of hyperbolas. Tomorrow we're going to do a little bit more with hyperbolas and see if we can figure out what happens if that center is not at 0, 0 how that affects things, move them all around, how that affects finding the asymptotes, and affects the equations. All right, so that'll wrap it up for today. More to come tomorrow.